Hey guys, I have your notes here for section 7.1 day 1. And what we're about to do is explore this chapter. It's called Differential Equations. And I'll tell you what differential equations are in a minute. But so far, you have taken antiderivatives either on your calculator. You've evaluated definite integrals on your calculator. And what that gave you is that gave you the area under the curve from wherever to wherever. Or another way to think of it is from an antiderivative perspective, you found the change in y values for that antiderivative. You've also done some integration by hand. And that's when I gave you a very simple integral. Something like a polynomial where you could easily do an antiderivative on it. Or a basic trig function, or a basic exponential function like e to the x, or something like that. So I'm gonna give you an overview of differential equations today, and then during the next several sections, I will show you how to integrate some more difficult functions by hand without a graphing calculator. Okay, so what is a differential equation? A differential equation is an equation that has an equal sign. It usually contains a function named y and its derivative named y prime. So let me show you an example of what a differential equation would look like. So I'm going to take you back to things we did back in section 4.2. In section 4.2, I walked you through implicit differentiation. This was when I gave you a function. It was not set up in y equals. So you couldn't just say dy dx equals and then do your derivative on the right. You couldn't solve it for y. This can't be solved for y. If it could, we would say y is some messy function. I don't know what it is, but it's some messy function. And I can't find it. But I want to do the derivative anyway. So we do implicit differentiation, which involves chain rule over and over again. So I'm finding dy dx. This is my clue that x is my variable. And so when I encounter a term that has an x in it, I do that derivative just like normal. Y is my function. Y is some messy function, and every time I encounter a term that has a y in it, I have to multiply by the derivative of the messy. I have to apply the chain rule. So here's what we would do. We would start out with the derivative of this term. The derivative of 2y is just 2, and then chain rule it, times dy dx. Now I move on to this term. I'm going to power rule it just like normal, and I get 6y to the first, but y is messy, times the derivative of the messy, equals, and then the derivative of this one is easy, it's just 4. And then you pull out a dy dx, and then you divide both sides by that quantity. This result is a differential equation. And I often abbreviate it and call it diff-EQ. And if you're moving on to, when you go to college, if you're going into like some kind of engineering, more than likely, you'll have to take a full semester course called Differential Equations. So you'll spend an entire semester on diff-EQ. So this is a differential equation. Notice this represents the derivative. So all of this is the derivative. And my original function named y, don't know what it is, we never found it, is in here. My actual derivative contains the original y function. That's a differential equation. Now, more derivatives that you've done before, you don't have to write this down, but you can call this y equals, let me make up something here. Y prime equals 4 plus derivative of sine cosine. Yep, you can call this a differential equation too. It's a derivative. It just doesn't, you don't see the original function in it, okay? But so that's a differential equation too, but we're going to focus on usually the more difficult ones that contain that unknown function, okay? Now, let me show you something cool. We'll look at this just a little bit, and then we'll revisit this concept that I'm about to show you later on in our DiffEQ section. So, I am giving you a differential equation. Here it is. Y prime equals 2 times the original function, whatever it was, over x. So, that's obviously a differential equation. It has my derivative and it has my original in it. Now, a solution to that differential equation is this. Now, you don't know that it's a solution yet. I'm just telling you that it's a solution, but here's what I want to point out. It's a y equals. So it's like an antiderivative of this, okay? It's called a solution to the differential equation. Notice that c is a constant. It's any constant. C is any constant. And so this is kind of funny. When we have a solution to a differential equation and it's got a c in it, gosh, c could be anything. So I don't just have one function here. I have unlimited possibilities of what this could be. This could be y equals x squared. This could be y equals 2x squared, y equals 3x squared, y equals pi x squared, y equals radical 7x squared. See? Infinite possibilities. This is actually called a family of functions. It's a representation of a whole lot of functions because it has a constant c in it that could be anything. It's a family of functions. Now, watch what happens. So I've just told you that's a differential equation and this is a solution to it. Watch what happens when I connect the two. So watch. I'm going to do a derivative on this. So I get y prime. Power rule. Wait a minute. This doesn't look like that. But here's what's kind of cool. Let's take y prime, which was 2cx. Let me put it right here in the y prime spot in my differential equations. So I'm going to go 2cx right there equals 2x. Now, also over here, since I subbed in y prime, let's look at what was y originally. What was y originally? Y was originally this pink function. So I'm going to take my original y and sub it in as well into my DiffEQ. Check this out. A pair of x's cancel, and I'm left with 2cx on the left, and I'm left with 2cx on the right. Yeah, those are equal. Okay, so what we've just done is we've just shown, we have just verified what I originally told you. Here's a differential equation. Hey, I think this is a solution to the differential equation. I've kind of just done a proof. I've kind of proved that this really was a solution to that differential equation because this original y fit in it and the y prime fit in it. And the equation was still true. Okay, anyway, enough about that. I'm giving you, here's a differential equation, doesn't have a y in it though. This one is actually a very simple one to solve. So it says, find the particular solution whose graph passes through this point. So when I solve a differential equation, I'm basically needing to do an antiderivative on it. When I solve a differential equation, I'm basically needing to do an antiderivative on it. And this I can do an antiderivative on very easily. Let's go. So antiderivative, I'm calling it y. And antiderivative of e to the x is e to the x. Antiderivative of this, I'm going to raise it and divide. And don't forget your plus c. All right, you know what this is called? This is called a general solution to this differential equation. So let's label some stuff here. This is a differential equation. This is a general solution to my differential equation. It's also, because it has a plus c, it's also called a family of functions. I know, it sounds funny, but it really is. A family of functions. Okay, but that's not what the directions asked. It didn't ask for the general solution. It said, give me the actual solution. So let's find the actual function without this unknown. Let's find the actual function whose graph passes through the point 1, 0. So a particular solution, I'm going to use this information that they gave me. I'm going to put 0 in for y and 1 in for x. A little weird, but that's okay. C is 2 minus approximately 2.7-ish. So that's my C value. So let's rewrite our general solution. Y equals e to the x minus 2x cubed plus c. 2 minus e. That's my particular solution that passes through the point 1, 0. Okay, now before we move on, I want to make sure you understand all this. So this was my family of functions. I did a simple antiderivative, and this is what I got. This was my family of functions. It's called a general solution. Now, here's what I did. I got out my graphing calculator, and I thought, I'm just going to play around with this just a little bit. I don't know what this constant is. Now, it's not exactly a y-intercept. Oftentimes, we think of this number as a y-intercept, and when we have a polynomial, like if this were just a cubic, that would be the y-intercept. But it's not exactly the y-intercept because it's not a polynomial. We've got to e to the something. When you sub in 0 for x, this term becomes 1. Okay, so it's not exactly my y-intercept, but whatever. It does change the height of the graph. And at this point, C could have been any number of things. Any number of things. So this represented a whole bunch of functions, a whole family of functions. So I just played around with it a little bit. Here's what I did. I made up some values of C. So I typed in my antiderivative, and I said, okay, let's let C be 0. So I did plus 0. So I just have y equals e to the x, right? What if C is positive 2? What if C is negative 3? And then I graphed them. So the highest graph was when C was positive 2. The lowest graph was when C was negative 3. And the middle graph was when C was 0. Okay? here's the thing. Each graph kind of has the same shape. That's because when you're looking at a differential equation, this over here represents the slope of your original. What do you mean by original? I mean the solution. I mean the family of functions. This represents the slope of your family of functions. So it doesn't matter what C is. The slope of this graph is always negative, negative, negative until some x value here, where the slope is 0. And then the slope goes positive, positive, positive until some x value here. And then the slope goes negative, 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 negative. Because no matter what this is, the derivative of this equation will always be this. So that represents the slope of all of them. Okay, so keep in mind, I made up several C values. So you know what this is? This is like a family portrait, because I have several different C representatives. Is this the entire family? Oh, good heavens, no. This is just 3 of them. This is just 3 members of the family. Does this family portrait include this guy? It doesn't. This guy passes through the point 1, 0. None of the 3 of these pass through the point 1, 0. Also, I found C from my solution to be 2 minus E. That was never one of the C's that I typed in up here. Okay? So when you have a plus C, that represents the family. When you use a point to find an actual C value, that gets you the particular solution. Alrighty, moving on. These are kind of cool. Without actually solving the problem. Okay, so here's what this is saying. Here's a differential equation. So this represents the slope of y. I know 1 point on y. 1 point is 0, pi over 2. Which one of these could be our y graph? This represents the slope of y. This represents a point on y. Which one of these could be our y graph? The first thing I would do is the easiest. Rule out any that don't pass through the point 0, pi over 2. 0, pi over 2, 0, pi over 2, 0, pi over 2. Well, that was pretty much useless. Okay, can't rule any out. Now let's look at slopes. No matter what I sub in for x, what I get out of it represents its slope. What if you sub in a negative for x? What type of answer do you get? What if you sub in 0 for x? What type of answer do you get? What if you sub in a positive for x? What type of answer do you get? I think every time we get a positive value. I think that this fraction will always be positive. It will never be 0. It will always be positive. So this shows the slope of y, positive, 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 0, negative, negative, negative. This cannot be the graph of y. This one shows teeny, but positive, 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 positive. This is the steepest that it gets. Positive, 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 positive. So this one's all positive. Can't be this one. This one's negative all the time. So I think that my answer is B. Next one. Kind of same concept. Which could be the graph of y if this is its slope? So it has to pass through -1, comma 1. -1, 1, check. -1, 1, check. -1, 1, check. Well, that was useless. All right, so check this out. Whatever x is, negative, 0, positive, when you do this math, you get the slope of y. When x is positive, the value of this is negative. When x is positive, the slope is negative. When x is negative, a negative in front of a negative makes a positive. When x is negative, the slope is positive. I think that one's B also. Almost there. Oh, I want to show you a really cool relationship between calculus and Pert equations. Remember, Pert represents exponential growth and exponential decay. So just a quick review from pre-cal. This is our initial value. So if we're looking at, I don't know, a population of a city, whatever, and its growth rate. This is our initial population at the beginning of our experiment. This is 2.7-ish. This represents the rate of growth or the rate of decay. When R is positive, the population is growing. When R is negative, the population is decreasing. And then T is time, either represented in days, months, years, whatever, however the problem is set up. This is always our ending amount. Beginning amount, beginning population, or whatever, ending amount or ending population. All right, watch when I do a derivative on a general Pert equation. I get y prime equals my constant. So remember, when I have a constant, I'm going to kind of pull the constant off and then go ahead and do my derivative. Okay, so I have a constant, and then this is e to the messy. What's the derivative of e to the messy? Well, the derivative of e to the messy is e to the messy times the derivative of the messy. Oh gosh, I got an r and a t. Think about this for a second. T is our variable. The derivative of r times t is just r. Let me rearrange this. Do you see that? This is exactly my original y. My derivative is my original y function times a constant. What constant? The rate. Or I can say y prime equals r times my original y. Now, do you know what all these letters stand for? I think you do. One more time. Original amount, rate, time, ending amount of whatever we're measuring. So let's say, let me go back to population. Let's say we're measuring population in a city. Beginning population, ending population, right? Rate of growth, time. Well, what's this? It's the rate of change of this. It's the rate of change of my population. It's how the population, how fast it's changing. So, I got y prime, rate of change, equals r times y. All right? An exponential equation is the only time this happens. So, hang on, time out for just a second. Let me take you back to Algebra 1 super quickly. Remember in Algebra 1 when you graph like y equals 2x? Remember how easy that was? Y equals 2x. We said in Algebra 1 that y was directly proportional to x. So whatever x was, y was always double that. No matter what x was, y was always double that. So when you have a constant times a quantity, we can say y is directly proportional to x. Okay, y is directly proportional to x. Okay, let's turn that into calculus and see what we got. We've got the rate of change for whatever, let's say of the population. The rate of change of the population, if this were a population problem, the rate of change of the population is directly proportional to the population. Okay, and I'm not being redundant here. I'm not saying the population is proportional to the population. No. The rate of change of population. The derivative is proportional to the function. The derivative is proportional to the function. The rate of change of the population is proportional to the actual population. So when you see that phrase, the rate of change is proportional to the original, you need to think, oh, that's calculus and that's Pert. Lock that in your brain. It's calculus. It's Pert. So let's do one real quick. Blah, blah, blah. The population is growing at a rate proportional to the population. The rate is proportional to the function. The derivative is proportional to a function. That's Pert. So let's see what we've got here. We had a population of 10 on May 1st. So that's kind of like my beginning of our experiment. So P is 10. E to the number of hornets grows to 50. Ooh, 50. In 30 days. See what I did there? I just pulled information out and stuck it in a Pert equation. How did I know to use Pert? Because it said the rate was proportional to the population. So there we go. And then it goes on to say, I don't know what R is. If the growth continues, when will the population reach 50? So it took 30 days for that to happen. When is the population, gonna reach 100? I don't know. Let's find out. First thing we have to do is find R. Let's work on finding R. I bet it's been a while since you've solved an exponential equation. I'm first going to isolate my exponential, and I'm going to divide by 10. So I've got 5 equals e to the 30r. I'm going to natural log both sides. And remember, when you natural log, you can take your exponent and bring it down to the front. Natural log of e is just 1. To find r, I'm going to divide both sides by 30. R equals natural log of 5 over 30. Okay, now that I know that, let's see what we can do with this information. How many days after May 1st will the population reach 100? Okay, now our starting amount is still 10. It was still 10 on May 1st. We want to reach 100. How long is it going to take to do that? So I've got 10e to the, now I'm going to use my r that I found, to the ln 5 over 30 times t. There you go. That's what we're trying to solve. So divide both sides by 10. Natural log both sides. Bring my exponents down to the front. Natural log of e is just 1. Now, I'm going to multiply both sides by the reciprocal. 30 over ln 5. 30 over ln 5. And I get, do the math. I think I ended up getting t's about 43 days. Okay, a lot of pre-cal involved in that problem. The only calculus that was involved was the phrase, the rate was proportional to the population. That lets you know that it was this type of original because it turned into this type of derivative. Alrighty guys, good luck.